Hello, good morning everybody. So, today we will continue with reactions in solution. Now, in the last lecture, we were discussing associative and dissociative mechanisms. Okay. So, associative and dissociative mechanism for solvent exchange reactions. Now, we talked about this which mechanism is operative. So, in that case we have to look into this activation parameters, and we have to make use of these equations, that is this del T of ln k p, which is equal to activation energy divided by RT square, and also del ln k del p t is volume of activation divided by RT. And see, for means we have got an example, two examples, that for gallium 3 plus and aluminum 3 plus, in one case for both of them it is delta H is positive, kilojoule 26.4 kilojoule per mole, and it is 113 kilojoule per mole, and delta S in one case it is minus 92 joule Kelvin inverse mole inverse, and in other case it is plus 117. First case for gallium it is minus 92, and for aluminum it is 170. So, looking at the sign of this delta S activation, we can see that the first case of gallium is the associative one. Why it is associative? Suppose we have got two entities of this sort. Okay. So, they are different. So, entropy wise, I mean there are two species, so entropy is expected to be more compared to when they are combining. So, difference is a transition from this state to this state. I mean, like let us take this like this. In one case the state is this, and the second case the state is this. So, initial state is this, final state is this. So, entropy for this transition will be less. I mean less means it is a negative, it is more, it is less. So, that means difference is negative, and in reverse case it is like this to that, this to that. So, it is less, it is more, so plus, I mean positive value. Okay. So, that is why we have termed this to be the 117 case to be dissociative and minus 92 cases to be associative. And also we have talked that delta V activation is more useful for understanding the solvent exchange mechanisms. This is a consequence of the fact that incoming and outgoing group, when they are same and are same means if it is water coming and water out, so there is not much change in volume of activation. So, it is neglected. So, that for the overall reaction delta V activation is close to 0. Now, volume activation is the volume delta V 0 transition state minus delta V 0 initial state. Okay. Thus, for a positive value of delta V activation implies an expansion to form the transition state, that is a dissociative mechanism. Okay. Dissociative mechanism means from here to here, and a negative value of delta V activation implies a contraction to form the transition state, that is an associative mechanism. Okay. This is an associative mechanism, and this is a dissociative mechanism. Okay. So, this bond is stretched for dissociation. So, you see this volume is initial volume, okay, initial volume is less, final volume is more. Here initial volume is this and plus this one. So, initial volume is total initial volume is more, and this is compared to this this is compared to this is less. This plus this is more than this volume. Okay. So, just by looking at this delta V activation, we can also predict whether this solvent exchange is a dissociative, or whether it is a dissociative or it is an associative one. Okay. So, proposed mechanism, reaction rates are determined determined by two steps: a rapid equilibrium, formation of an ion for an ion pair case. Okay. Say even if it is your ligand is water or not. Okay. So, rapid equilibrium formation of an ion pair or outer sphere association complex if the ligand is uncharged or positively charged. Okay. A subsequent rate determining interchange step, where the ligand makes bond to the cation after release of water molecule from its primary coordination sheath. Okay. So, this is an equilibration, formation of the outer sphere complex. Okay. Then ligand exchange process. So, separate ions, outer sphere complex, inner sphere complexation. Okay. So, this can be written in this form, that MH2OX n plus. Okay. X number of H2 is there with charge n plus ligand, formation of an outer sphere complex producing this, then ligand exchange process giving rise to MH2O X minus 1 L plus water. So, water is expelled out. So, initially an outer sphere association, okay, followed by in the subsequent rate determining step the ligand gets in and a water is taken out. So, this is a proposed, or it is a plausible mechanism for this ligand exchange process. It may be water, it may be something else other than water as well. Okay. So, rate equation is this. So, it is a two-step process, like as I talked about while I was discussing this diffusion control reaction, where we have got the similar type of expression, that ddt of mLn plus, that is rate of change of concentration of this, which is equal to KOS outer sphere complexation equilibrium constant, then interchange ligand exchange rate constant. Okay. Just look into this, okay, divided by 1 plus KOS, but when the concentration of ligand is less and generally KOS is small, that is equilibrium constant is small value, then you can neglect. So, your expression becomes KOS Ki into this. So, rate is dependent directly on the metal concentration and also the ligand concentration, provided this denominator, this part KOS L is small. Okay. So, this is the rate expression corresponding to this this mechanism, that is corresponding to this proposed ligand exchange mechanism, initially the formation of outer sphere complex, then inner sphere complex formation. Okay. Then we will move on to electron transfer reactions. Okay. So, what is an electron transfer reaction? Electron transfer reaction is typically a redox reaction, oxidation reduction reaction. Okay. There are many examples that you can think of. Okay. Say like copper sulfate. Okay. Copper sulfate is electrolysis is made when copper sulfate solution is electrolyzed solution, or maybe molten copper sulfate, okay, or maybe molten sodium chloride by using 2 electrodes. Then sodium plus is converted to sodium 0. So, it is the reduction of sodium plus to sodium, okay, or maybe ferric chloride, okay, ferric chloride plus say stannous chloride, giving rise to ferrous chloride and stannic chloride, okay. So, that means in that case it is a reduction process of ferric to ferrous and oxidation process of stannous to stannic. So, that means what is happening, that when it is an electron transfer process, one entity is transferring electron to the other. So, the one which is giving the electron to the other entity is getting oxidized, that is, it becomes electron rich because it is accepting the electron and it is giving out the electron. So, electron deficient becomes electron deficient, or maybe its oxidation state is increased and its oxidation state is decreased, okay. So, that means whenever there is an electron transfer process, you can have a pair of substances or pair of chemicals which undergo oxidation and reduction process. So, electron transfer process is generally therefore a redox process, okay. One entity is oxidized, the other entity is reduced. So, this reaction, this redox reaction, okay, can take place in ground state. Ground state means molecular ground state, that is the lowest energy state that may happen, okay. As I told you that ferric to ferrous and stannous to stannic, it occurs in the ground state, ground electronic state, or in some cases this electron transfer may occur in the excited state. So, that is called the excited state electron transfer process, as what I have talked about in case of exciplex formation. So, it is an excited state complex formation via electron transfer from one entity to other, but not in the ground state. It is in the excited state, not in the ground state, but in the excited state, okay. That is, say your molecule first gets excited to some level, and in the excited state the species has got more tendency to transfer the electron or to accept the electron. Since excited state properties are a lot more different than the ground state properties, it has been found in most of the chemicals, most of the molecules, that excited state properties differ considerably from the ground state property, because excited state electron distribution within the molecule is different, that is, orbitals differ than what is in the ground state, okay. That is why the excited state properties are different, therefore, excited state electron transfer or electron acceptance in these tendencies are different, okay. So, that is about your exciplex or excited state complex formation. A typical reaction, scheme for electron transfer is like this: A plus, a charge A plus, A plus, plus charge plus B, giving rise to A plus B plus, or maybe say A plus B, say electron is transferred from here to here, giving rise to A plus B minus, or maybe A plus plus B minus, okay. So, it is a bimolecular case, bimolecular reaction, okay. So, rate of the process is equal to K into concentration of A plus into concentration of B, okay. So, if it is an elementary step, then since two species are involved, therefore, rate is equal to K times A plus into B. Okay. So, and also maybe if it is an elementary reaction, the same way you can write. Okay. So, this is a typical representation of an electron transfer process. What happens in case of your excited state process? Say you have got a molecule which does not react in the ground state. Okay. So, that means A, then what you have to do? You shine with radiation, appropriate radiation, it moves on to excited state, maybe singlet. Then in the excited state, if you have got, say, if you have got some suitable electron acceptor such that say maybe electron acceptor of this sort, then you get A, B, maybe plus, minus, and maybe it is a complex. So, this complex formation occurs in the excited state, which is called the exciplex, excited state complex, and then it will undergo various other reactions, maybe some photophysical process or maybe some photochemical process. It will undergo some photochemical or maybe some photophysical process. Okay, so this is about your excited state process, this is about maybe in the ground state process. So, electron transfer reaction can happen in the ground state or maybe in the excited state as well. So, depending on the species concerned. Okay. It is not that for all species ground state electron transfer will take place. In some cases it has been found that in ground state there is no reaction, but if you shine with radiation, the reaction takes place, because in that case in the excited state the redox properties are different than the ground state redox property. That is why you need to excite the sample, and then redox properties are altered, and then other reactions will automatically occur. Okay. Typical examples: ferrous ferric case, ferric aqueous plus ferrous aqueous giving rise to ferrous aqueous ferric aqueous. It is an electron transfer between ferrous ferric. It is 3.3 mole inverse second inverse. Ferric plus chromium 2 plus, okay, chromas, then ferrous plus chromic. Okay, its rate of electron transfer is about 10 to the power 2.3 into 10 to the power 3 mole inverse second inverse. For ferrous ferric it is 3.3 mole inverse second inverse. Now, what happens with ferrous hydroxide with chromas? Then it becomes ferric hydroxide FeOH 2 plus. It is basically ferric with one OH and chromas. Then you see it is giving rise to FeOH plus and chromic. So, because it is OH, presence of OH, you see its value is high, 3.3 into 10 to the power 6, whereas only equated or hydrated ferric is doing it at a lower rate. So, therefore, this redox properties are very much dependent on, you see from this you can say that since these two, although this is iron 3 plus, this is also iron 3 plus, but you see the rates are considerably different, means it depends on this electron transfer tendency. Electron transfer reaction is very much dependent on the ligand concerned, not only on the oxidation state or the charge, but also on the ligand present. Is very important. Okay, so the crossing of activation barrier for redox reaction does not proceed, and diffusion control limit, say 10 to the power 10 mole inverse second inverse, and also the size of the barrier is affected strongly by ligands. Okay, as I told you, means from this example, the size of the barrier is affected strongly by the ligands, which indeed influence the rate constant K and the redox potential. Okay, so ligands play a vital role in controlling the rate of electron transfer. That is, crossing of barrier is very much dependent on the ligand, and also the crossing of activation barrier for redox reaction does not proceed at the diffusion control limit, which is of the order of 10 to the power 10 mole per second inverse. Okay. This is another observed situation. Okay. Now, let us again consider this electron transfer from a donor to an acceptor, D plus A giving rise to D plus and A minus, where velocity of the reaction, velocity of the reaction is, since it is an elementary process, as I told you, we started with A plus plus B, but here we are uncharged state to a charged state. So, velocity is k observed into concentration of A into D into concentration of A, and also if we assume that it proceeds via formation of a dA complex, that is donor acceptor complex, followed by electron transfer, that is an equilibrium is established between A plus D to AD or D plus A to dA, an equilibrium is established, then electron transfer takes place to give rise to your D plus A minus. Okay. So, equilibrium constant will be like, this is an equilibrium, k dA is equal to dA divided by dA, which is your Ka divided by Ka primed. K is the association rate constant and Ka primed is the dissociation rate constant. Okay. Next is the step is as I told you, that it is the electron transfer within dA complex. So, the thing is that these two entities initially will form a complex, say this is the complex, and then after this is formed, since now orbital of say donor and orbital of acceptor, they somehow they interact. So, proximity, because of the proximity. So, now it is this interaction is well suited when they form a dA complex, and then transfer of electron from one to another takes place. So, that is why next is the electron transfer that is occurring within dA complex. Okay. So, rate of electron transfer, that is the rate of electron transfer means the rate of reaction, electron transfer reaction is basically V electron transfer, which is equal to K electron transfer into concentration of dA. Okay. Now, this dA, D plus A minus has two fates, one is back electron transfer or reverse electron transfer, and then other option is the dissociation. So, dissociation of this D plus A minus. So, the moment the electron is transferred from donor to acceptor, they become charged, one becomes plus, another becomes minus. So, they are held by electrostatic force of attraction. Okay. And then solvent cage, what that will do, that will interfere in between, so that followed by they will separate. I mean, the solvent will enter in between D plus and A minus. Okay. And their attraction force becomes less, so that they will tend to separate out. But in the meantime, other situation may happen immediately after the electron is transferred from one to another, that is D to A, reverse electron transfer may take place, or the back electron transfer that may take place. So, that is depicted here, I mean that is written here as V reverse is K reverse D plus A minus, so that the contact dA pair is regenerated. Okay. The other option is that, as I told you, that after the electron is transferred, they will, I mean D plus A minus will separate out, producing isolated D plus and isolated A minus. So, that rate is dissociation of your D plus A minus is Kd into concentration of D plus A minus. Okay. So, what has happened is we started with a donor and an acceptor. Your result is D plus plus A minus separated. Overall rate is K observed is, B observed is K observed into dA. Okay. So, what is happening that it occurs via formation of a dA complex. So, like this, D plus A dA, then D plus A minus, then it has got two options, or maybe I can write like this, reverse electron transfer D plus plus A minus. Okay. So, it is your KET, this is your KR, this is your KD. Okay. And this equilibration, this is your KDA, equilibrium constant. Okay. So we can finally write like this, that 1 by K obs equal to 1 by Ka, 1 by K OBS observed is equal to 1 by Ka plus Ka prime divided by Ka KET times 1 plus Kr by Kd. Okay. When Kd is very greater than Kr, what is Kd? Kd is the dissociation rate, okay, compared to your reverse electron transfer rate. When Kd is much greater than Kr, okay, then what we can write, 1 by K obs 1 by Ka into 1 plus Ka primed by Kat. Okay, when Kd is very greater than Kr. So, this is one case when this is high. Okay. So, means from this you can get this expression with the idea that Kd is much greater than Kr. Okay, when Kd is much greater than Kr means this is negligibly small. Okay, this is negligibly small means in that case this 1 plus Kr by Kd can be approximated to 1. Okay, therefore you just have this one. So, this one can be written as 1 by K obs, which is equal to 1 by Ka plus approximated Ka prime divided by Ka Ket, which gives you this one. Okay. What about the other situation? Okay, what about the other situation that when Ket is very less than Ka primed? Okay, when Ket is very less than Ka primed means what is Ka primed? Ka primed is this is the association rate constant divided by dissociation of A. So, your expression is when Ket is much less than Ka primed. So, your original scheme was like D plus A, original scheme was D plus A, your Ka and your Ka primed, dA, Ket, Kr, d plus A minus Kd, d plus A minus. So, this one, this situation means if this one is very high compared to the forward reaction, okay, then what would you get? Your original expression one was 1 by K obs is equal to 1 by Ka plus K primed divided by Ka Ket 1 plus Kr by Kd. So, K obs will become, in this case after applying this over here, K obs will become Ka by Ka primed into K Et. Okay, that means your K primed, if K primed is very high compared to this one, okay, then if this is a very high quantity, then compared to other, this is major. Okay, this part is the major share. Okay, so therefore this expression can be approximated. So that means 1 by K observed is equal to your K prime divided by K Ket, just this part. So that will give you this one. And using the transition state theory, Ket electron transfer, you can write like this, Now, mechanism of redox reactions. Let us come to mechanism. Outer sphere mechanism. Okay. The redox state postulated is simply the electron transfer between two reactants whose primary coordination sphere remain intact throughout. An elegant theory is based on this correlating, this is the Marcus theory. So, primary coordination sphere is not affected, only the outer part is affected. So, it is your outer sphere mechanism. Now, let us draw an energy versus reaction coordinate diagram, energy level diagram. The curve represents the energy of the system along a particular configurational coordinate. That configurational coordinate may be average metal ligand distance, that is the complex in the left hand side in your reaction scheme, and the average metal ligand distance, okay, in the complex which is in the right hand side. Okay. So, the possibility, this is your energy, this side is your energy, this side your reaction coordinate, and this is your energy of activation. Okay. And it is a symmetric electron exchange case. There are two possible ground states in either of which the reduced form of the complex has a greater metal ligand distance than the oxidized, maybe here greater metal ligand distance. The orbital overlap between these two states leads to level splitting at the midpoint. Okay. So, it is a case of symmetric electron transfer, and this is your energy of activation. So, this is E star, okay, E star, and then it will move from this potential energy surface to this potential energy surface. So, this much of energy has to be applied over here for for transition from here to here. Okay. So, the reaction, electron exchange reaction can thus occur by one of two mechanisms. Okay. As I told you that maybe E star means the amount of energy that may be supplied by by a photon, or maybe by second means. So, absorption of a photon, that is energy E star, with a consequent electron transfer from product and to form the products in an excited state, that is common to the bridge system. That is, the system absorbs a photon and then electron is transferred, as I told you in case of your exciplex formation. Okay, so absorption of a photon with energy E star, and thereby the system is transferred from a state of a given oxidation state to another state. Okay, so that is occurring by electron exchange, or electron exchange proceeds by thermal activation. Okay, so it is a photochemical activation. Okay, a small amount of energy is used to shorten the metal ligand distance of the larger complex and to lengthen the distance in the smaller complex, making them structurally symmetric. At this point, the electron is delocalized and transfer may occur. Okay, and so this is the basis of Marcus's theory. Okay, so it may be by thermal means, or as I told you, it may be by a photochemical means. Okay, so electron exchange may be by this means, or maybe by small energy that is supplied from the thermal energy that is available within the system, that is kT. Okay, and what about the other mechanism, inner sphere mechanism? The reaction between M plus M n plus occurs with a bridging anionic ligand X minus. So, there is an X minus, so which bridges. Okay, that bridge may be water, as OH minus, or maybe water like, not exactly water is not a good bridging one. So, water cannot be very good, and some cases there are examples, but water compared to OH minus is a poorly bridging. OH minus is a good bridging one. Okay, the bridging group X minus can be one of a variety of ligand. Okay, the one essential feature of a bridging ligand is that it should have at least one lone pair of electrons available for interaction with n plus, in addition to those used to coordinate with m plus. Okay, so this X minus will coordinate with a pair, and there may be an additional pair which will coordinate with n plus. So, it should have sufficient option to coordinate with both m and n. That is why the bridging group has the essential feature that it should have at least one lone pair of electrons available for interaction with m plus, in addition to those used to coordinate with m plus. Okay, so often bridging group is transferred during such electron transfer process. Okay, like as I have given over here, that A plus dot x it is initially coordinated plus B, then electron is transferred, this one has got transferred from A to B, and of course the electron has been transferred from B to A, thereby making A plus to A0 and B0 to B plus x. Okay, so it occurs. So, in inner sphere mechanism, so it happens via a this reaction happens via bridging ligand X minus. Okay. Now, typical example I am citing over here is, say, it is a cobalt NH3 plus Cl 2 plus chromium 2 plus equated plus 5H plus, giving rise to this. So, what is happening over here? This chloride, this is coordinating over here. Okay. So, chloride has got, chlorine has got lone pair of electron. So, you see, as I mentioned over here, that at least it should have at least one lone pair of electrons available for interaction with Mn plus, in addition to those used to coordinate with M plus. You see here this chloride is already coordinated to cobalt. Okay. So, now it has got a lone pair. So, that lone pair is, this lone pair is given to here. Okay. I mean, this outer circle represents your lone pair, I mean electron cloud, and of course, lone pairs are present. So, that lone pair is donated over here. Okay. And of course, this bond will be a little bit strengthened, because now this is going to become a bridging ligand. So, it comes over here, and then automatically it's a kind of as I told you, like associative mechanism kind of thing, that the moment the chloride comes, this bond may be lengthened, and then it is, this water is expelled. So, this attacks over here, then water is expelled. It is a kind of SN2, although it is not from the, may not be from the back side. Okay. So, that happens, and then now what is happening, that because of this bridge formation, these two interacting entities are now in close proximity. So, now it is good time for them to transfer an electron, because they are now in close proximity, because it means in some cases solvent mediated electron transfer may happen, but probability wise that is less. Okay. But the one which is more probable is that when these interacting entities are made to come close to each other, then this electron transfer is rather facile. So, facile electron transfer from here to here, this is happening because of, say, such bridging interaction. So, for some time this chloride will tend to bring these two entities here, like cobalt and chromium, okay, in a proximity, and then electron is getting transferred. Okay. So, electron is getting transferred. So, this is your this is the typical transition state. This is the typical transition state, that chloride is a bridging one. Okay. So, after it is transferred, initially cobalt, it was cobalt 3 chromium 2, now it is, electron is transferred, means it is getting oxidized and it is reduced. Okay. So, redox reaction, I mean electron transfer has occurred via this bridging chloride, and then ultimately this will separate out. Okay. So, of course, it will separate out, and the ligand leaves cobalt, as I told over here, that often bridging group is transferred during a reaction. So, the example here is, this bridging group is transferred over here. Here you see also this bridging group, initially it was associated with cobalt, now it is a part of chromium. So, bridging group is transferred from cobalt to chromium along with the electron transfer, which results in redox between cobalt 3 chromium 2 giving rise to cobalt 2 chromium 3. Okay. Okay. So, this transfer of ligand is facilitated by the presence of, this does not always happen. So, the moment this chloride is a part of chromium, this transfer is possible because of the labile cobalt chloride bond compared with chromium cobalt, I mean chloride bond. Cobalt 2 chloride bond is more labile compared to chromium chloride bond. Okay. So, depending on whether this bond is stronger or this bond is stronger, the ligand, I mean the bridging ligand, will either remain to its original site, or maybe it is transferred to the other site. Okay. So, this is there are plenty of examples that you may find in literature, or maybe in many books, where you will be finding involvement of bridging ligand, like OH minus. OH minus is also a very good bridging ligand, but not, water is not that as good as as good as OH minus. It is a poorly bridging. Okay, so bridging ligand is a very important part for inner sphere electron transfer process to occur. Okay, and pH dependence is also this electron transfer is also very much dependent on pH of the medium. So, pH can also play a crucial role in determining the electron transfer rate. Okay. So, as we have talked about here, that electron transfer reaction is a very crucial reaction. Okay, that is a redox reaction. So, in chemical, also in biochemical systems, okay, electron transfer plays a very important role. Okay. Now, because of electron transfer, a species is oxidized or reduced, and correspondingly the other species is reduced and oxidized. Okay. So, you will be finding a plenty of biochemical reactions, like in case of respiration. Okay. So, what I mean, oxygen is used, okay, to oxidize, and as a result of oxidation, enormous amount of energy is released. Okay. So, that is also a redox process which occurs inside our cells. So, energy is released and that energy is used up for doing some work, and that is why you eat and we gain energy out of the food. So, in biochemical reactions or biochemical processes, this electron transfer process is a very crucial reaction. Apart from other there are other reactions like hydrolysis, then maybe a ligation or whatever. So, those are also important, but this reaction, especially in respiration, is very important reaction. Okay. And apart from this biochemical processes, maybe chemical for chemical processes as well, redox reactions play a paramount role. Maybe industrial processes, this electron transfer reaction is a very important reaction. Okay. So, so let us come back and what we have learned over here in this under the heading reactions and solution. Okay. Now, we have talked about this solvent exchange reaction, okay, associative or maybe dissociative solvent exchange reactions. Okay. Now, we can identify by looking at the activation parameters whether the reaction is an associative solvent exchange or it is a dissociative solvent exchange, and by the use of the thermodynamical concepts, okay, concept of entropy. Okay. The entropy is basically nothing but it is a measure of degree of disorder. Okay. So, when activated complex is formed, okay, if it is an associative mechanism, that means maybe more than one species, they combine to form an activated complex. Okay. So, initially you have 2, finally you have 1. So, there are more option for these molecules, 2 molecules. I mean, the system can be represented in many ways. That is, there are many ways of realizing the system, but when it is only one species, that ways will be reduced. Okay. So, when it is an associative case, then of course entropy is released, because entropy is a measure of degree of disorder. Okay. So, when it is associative, reduction in entropy; when it is dissociative, more species, increase in entropy. So, from this we can find out, looking at the activation parameter, we can find out whether it is an associative or dissociative. Okay. And from the volume of activation we can also from the volume of activation we can also know whether when it is a negative or whether it is its value is positive. We can find out whether it is an associative or dissociative process. And we have talked about the proposed mechanisms, the rate equations. Then we jumped onto electron transfer reaction, which is a very important phenomena, especially in solution phase. Okay. We discussed that with several examples, and we also talked about their kinetics and how that can be affected, factors that is going to affect, and different situations, like when Kd is very greater than Kr, or when K electron transfer is very less than K dissociation of your donor acceptor contact complex. Okay. And we also try to understand the various mechanisms, maybe outer sphere or maybe inner sphere. Okay. And possible means of reaction, whether it is absorption process, whether it is via absorption of proton or by a thermal means. Okay. Inner sphere mechanism we also try to explain, and in that case we have taken the example of this, where chloride is acting as a bridging ligand for facilitating electron transfer, and at the end of reaction chloride is getting transferred from cobalt to chromium. Okay. So, that is all about electron transfer reaction. Next, in the next piece of lecture we will talk on electrode kinetics, because electrochemical reactions that is occurring at the electrodes, because at the electrode electron transfer takes place. So, metal ion becomes metal, or metal dissolves into solution. So, that is a very important reaction, that is important part of kinetic study, that is the kinetics of reaction that is occurring at the electrode. Okay. So, we'll take up that in the next class, in the next lecture, that is the electrode kinetics. So, that is all for today. Thank you.